طيب, Bismillah ar-Rahman ar-Rahim. So we're still talking about trace route, and we said that trace route, like ping, is used to troubleshoot the connectivity to a certain destination. Trace route gives you the probable route to the final destination from a certain point, from your local host all the way to the final destination. It gives you the probable host, because we said that this probable route might change from one time to another, and also even the return from the final destination may take a different route. So the trace route uses a certain hack of the system using Cmpe protocol. So the Cmpe protocol is used, through like a trick that the trace route does to give you information about every single hop in the route end to end. So the idea here is that the trace route performs like Cmpe request and response using we said that Cmpe is encapsulated into IP directly, right? So the trace route, what it does is that it uses a certain aspect of IP to restrict the Cmpe message to go one hop at a time. So the first time it goes to the first router and then it sends you a reply. So the idea here is that we want to get a reply that we have visited every single hop of these. So how do we do that? Because Cmpe itself will give you one reply from the final destination, whether the final destination exists and everything is working fine or not. But we need a reply from every single hop that we have passed through this router, we have passed through this router, we have passed through this router, and so on. So the idea here is that trace route will use Cmpe in a certain way by setting what we have called before the time to live. Remember the time to live field? That field is used to restrict the number of hops that any message goes through. So the idea here is that if we set the TTL to 1, then we restrict the message to go up to this router and it stops. Okay? But then it stops with an error, right? So the error is, time exceeded, or I have, exceeded the time that this packet will remain in the network. Okay, so this is the hack. So we will hack and recognize this time to live or time exceeded error as, everything is fine. So that's why I said that it hacks the Cmpe message request and reply.
I have a question about TTL. What if the packet needs to, for example, the TTL in a certain header is, for example, 32.
Right.
And it needs more than 32 hops to reach the destination. How can we specify the TTL?
We set the TTL to the maximum number of hops that we think this packet can go through. So if this number is low, 32 as we said, and the packet needs to get to the destination using more than 32 hops, then tough luck, the packet will be dropped. So in that case, you would want to set the TTL to maybe it's like 500, 300. I mean, doesn't matter. But setting this number to a high number, of course, may cause the fact that this packet will circulate in the network unnecessarily. But you want to avoid the fact that it will be dropped unnecessarily, and this is a major damage.
So, Doctor, can you look in the routing table and know how many routers or how many?
The routing table does not give you that. Remember,
Yeah,
the routing table does not give you the global picture.
Yeah. Uh-huh.
Routing table tells you that if you want to go to Al-Sad, you need to get right. That's it.
Yeah.
But whether you will go to Al-Sad by turning right or not, that's not my problem. So think of a router as, like one sign in a roundabout that tells you go this way, go this way, go this way. But I'm not responsible of the consequences that will happen later on. I don't have the global picture.
Okay. So you mean only it's telling me the IP addresses that are connected to my next router.
Right. Only my next router, yeah. And then it's up to the next router to give you the instructions for after that. But my job is done once I tell you. That's why routing is eventually done through packet forwarding. We call it packet forwarding because eventually I'm not going to give you the end-to-end route. The only one who knows that is like if you have like Google Maps or something like this. But the router itself doesn't have the global picture. Okay. So going back to traceroute, so the format of this command is very easy. You say traceroute and you give it the destination IP address. But what you don't want, what you want to get here is not only the fact that this destination address exists. I want to know the actual, hub-to-hub route, how to get to this destination. So to that, what we need to do is that we formulate an ICMP message, okay, and we use the TTL field in the IP header, okay, and we send a UDP message or a UDP header with any destination port, with a destination port, with an arbitrary destination port. And I will tell you the function of this later, okay? So ping didn't have to use any UDP part, right? For the ping, we didn't have to use any UDP part. But here, we have to, because eventually we want to know that we have reached to the final destination. So remember the router does not have a transport layer at all, right? So all the routers, they will not process this part until you get to the final destination. The final destination will then process this UDP header. And then it depends. If there is an application running with this destination port, then it gives you a reply back that, everything is fine. I was able to find the destination that you want. Or if there is no application running on that port, then it gives you what? Port unreachable. You have reached to the final destination, but no application is running for that port, so the port is unreachable, right? Port unreachable is part of the destination unreachable error codes that we talked about last time, okay? So whether you get, the application is running, or you get port unreachable, you recognize this as, this is the end, so you don't want to use the TTL anymore. And I'll tell you the step by step. So step by step, so we set the TTL initially to 1. So when we set it to 1, the maximum number of hops that this packet will transfer is 1. It gets to this router, and then this router will reply back. So the reply back, remember the reply was had a type of 0, but this one has a type of 11. Which indicates that this is not an actual reply, this is an error message. And this error message indicates time exceeded. Okay? So the request for ICMP had a type of 8, and the reply had a type of 0. This has a type of 11. 11 is not actually a normal reply, it's an actually error message that indicates time exceeded. Time exceeded indicates that the TTL has reached to 0 and I cannot forward it anymore, so I'm just sending you back an error message that time exceeded. So I will interpret this error as, this is the of course, when it sends you a reply back, it gives you the IP address of that particular interface of the router. It gives you a reply back of this, so it will be 10.0.0.2, right? So the reply will come from 10.0.0.2. It will be received by the router A. Okay? So the source will be, as you can see here, 10.0.0.2, and the destination is 10.0.0.1. Okay? And the type is 11 to indicate that time exceeded. So I will. So what I will do now is that I have received from this address, which is not the actual destination, because I have the actual destination, right? So what I can do now is that I can tell you the first hop you will probably take is 10.0.0.2. Okay. So what will happen is that when you say trace route and you give it the destination IP, you will get the first line first. The first line is 10.0.0.2, and I received this in 4 milliseconds. Okay, so what happens is that traceroute sends, for each packet, it sends 3 copies. So it sends 1 packet and come back, send 1 packet and come back, send 1 packet and... So 3 of these packets they take, and for each one, I have to report the round trip time. So I sent it at this time, and I received it after 4 milliseconds. So I report that I received a reply from 10.0.0.2, and all the 3 packets that I have sent have taken 4 milliseconds to go and come back. Okay, so this is for the first hub. So what do I need to do now? What do you expect should be done now?
TTL should be 1 again. So
1 again? 2 back. Okay. Okay. So when I set it to 2, it will go to this router. This router will forward it 1 time, right? So it will go to this router C. This one will send back an error message that, time exceeded, and I keep doing this. Okay? So when this replies back, it will reply from an address which is a 172.16.0.2. Right? So the reply back will come from this IP address, and then I will have the round trip time, which I can calculate easily. I set the time where I send the ping message or the ICMP message, and then I record the time when I received the reply. I subtract this from this. I know how much time it took to go back and forth. So I set the TTL to 2, send it all the way to router 3. So when I set it to 2, it will pass router B and it will go to router C. Then I reply back from 172.16.0.2 with, again, time exceeded. Okay? So I keep doing this all the way to the destination. When it reaches to the destination is 192.168.10.2. This is the actual destination, right? So I want to send it to this destination. Then, and only then, it will send it up in the transport layer, to the transport layer. So the transport layer will then check whether there is an application running with a port 35,000 or not. And it's, if you're lucky, maybe there is an application running that will reply back with something, or you will get an error that destination unreachable, which has a type of 3 in that case, and then the error code will give you whether port unreachable or network unreachable, and so on and so forth. And then you will interpret this. As long as the error is not time exceeded, then you know that you do not want, you should not increment TTL any longer, right? So you keep incrementing as long as the error coming is a time exceeded. Once the arrow changes, then you know that you have hit the destination, you stop. Okay? So this is the criteria to stop. That's why I said it's a hack. It's you get error all the time, yet you through the error code you sort of get some idea whether you have reached the destination or not.
And when we reach the destination, the type will be 8.
The type will be 3, or the type will be 0, which is if there is an application running, then the reply back is everything is fine. Or if there is no application running, okay, which is the most probable possibility, that there is no application running on this port. In that case, the error will be, or the type will be 3 to indicate that destination is unreachable. And in that case, the code will indicate the error code, which in that case is port unreachable. I don't remember the number of the code for port unreachable. Okay, so in that case, type will be 3 and code will be 3 to indicate that port is unreachable. Okay, so that's how it is. So that's So once you receive port unreachable, this is the criteria for you to any So for each one, for each hub, you just need to report where you got the reply from to indicate that. First, you will go through this hub, and then this hub, and then this hub, and so on. And for each one, you send 3 copies, and you calculate the round trip time. Sometimes the round trip time might slightly change. Okay, so if you have the response round trip time equal like this, so this indicates that the connection to this particular host is stable, right? So this, it doesn't go up and down, or there's no actual traffic that affects the response back and forth. Okay. Any questions?
أنا في الفرق بين التايب والكود يعني in this ICMP.
Yeah. So the type. We have type 8 to indicate the request, type 0 to indicate the response, and I have no idea why they didn't make it 0 and 1, for example. But
0.8 diamond type.
0.8, this is the request and reply. Okay. Other than that, it's just a category of error. Yeah. So if the error is like, you can categorize the different errors into special categories. One of them is error related to the IP header, which is like time exceeded and so on and so forth. So that takes the type 11 as it's set here. If the error category related to the fact that the destination is unreachable, whether it's a network unreachable or port unreachable or code, or the protocol is unreachable, and so on. This is type 3, and so on. So this is the standard, and sometimes you have, these error codes, you can assign them with great flexibility. So the designer was the one who actually assigned these codes like this, and they have used it as is. Okay, you want to keep it as is because you're talking about a protocol, and if you change these error codes,
means you're not following the protocol.
You're not conforming with the protocol, which means that you cannot talk ICMP with anyone else. So, but initially you had all the flexibility to assign whatever error codes and request and reply as you wish. For example, in chapter 9, we will discuss a similar protocol, okay, which uses request and reply as 0 and 1. So it's not. But once you set it like this, you have to keep using it as is. Otherwise, you're not conforming with the standard. So that's it for chapter 6. So chapter 7 is pretty small. It talks about data link layer. Data link layer, of course, is layer 2. And as we said, for TCP IP model, it's part of the network access layer, which maybe half of you did not answer this correctly in the quiz. unfortunately, and it was really surprising. So the network access control is divided into two layers, which is the physical layer and the data link layer. Okay, so now we will, of course, we're going from top to bottom. So first we address the application layer, which is the first three layers, and then we talked about transport layer, network layer, and now we'll talk about data link layer. Next chapter we'll talk about physical layer. So the data link layer provides the means for exchanging data over a common local medium. So data link layer is the first layer that deals with the physical topology of the network, in the sense whether you are talking about fiber optics or wireless or something like that. Because up to IP, up to the network layer, we didn't care much about the actual local medium. We didn't mention what the local medium could be. We don't care, right? The only thing we talked about is that maybe there is one certain parameter which is called the maximum segment size.
Yes.
that we need to know about, so that we know whether or not we need to do fragmentation. But other than that, we don't care, right? And that's one parameter. It's correlated with the medium type, but it's one parameter that abstracts this medium type into just one segment size, and that's it. But I didn't have to deal with the characteristics of the medium in any way. Data link layer is the first layer that starts to focus on the type of medium, and based on the medium, it actually changes its functionality quite a bit. So it's responsible for connecting two devices, whether these devices are host, router, switch, hub, whatever. So it's responsible for connecting these intermediary devices together to form the end-to-end communication. Certain protocols or standards in the data link layer are Ethernet, which we will cover it in details in chapter 9, and then point-to-point protocol, which we will just talk about briefly in this chapter. ISDN, which we will not talk about, and frame relay. So these are some of the standards or international protocols that are used as part of the data link layer. So as we said before, the data link layer creates what we call a frame. So the protocol data unit in the data link layer is called the frame. So the first thing that the data link layer does is what we call framing. So it provides a framing service to the upper layer. So the upper layer is the IP, and then this gets encapsulated into a frame data and header and trailer. So data link layer is the only layer that has a trailer in addition to the header. Okay, this is the only exception. Other than that, we always talked about only a header but no trailer, right? So the header is, as usual, it uses like addressing, and it uses a type which tells the upper layer what type of protocol exists in the upper layer, which is, of course, 99%, it's IP. And of course, some quality control, which we will talk about. The trailer itself has error detection codes. So error detection is done as part of the trailer in the data link layer. The reason is that the error detection in the data link layer is quite complicated. It's not only based on checksum like TCP and UDP. No, it's quite more complicated than that. And in some cases, it includes error correction techniques as well, not only detection. So here, you want to detect all possibility of errors, all types of errors. Checksum usually gives you like a parity which tells you if there is 1 bit in error. But if there are 2 bits in error, then you will not discover the error. But here, I want to I want to make sure that all types of errors can be detected. Why? Because, well, if you have any error in the frame, there is no point of continuing any further, right? There's no point of sending this frame any further up to from this point. So if there is any error, just drop the frame, discard the frame, and rely on higher layers to retransmit and do whatever. But you don't want to keep the network utilized and busy with something that has an error. So that's why you want to really discover all types of error on a point-to-point basis. So the data link control provides the communication or the node-to-node communication within a LAN, and then from this point to this point, or from this point. So I want to send, for example, information from this node all the way to this node, مثلا, for example. So in that case, data link layer using the physical address that we will talk about will provide the communication point to point, and then here from point to point, and then here from point to point, and so on. So it gives you point to point communication over a LAN or a WAN. So this is a LAN and this is a WAN. Okay? So this uses some type of a switch, and a switch gives you some sharing medium. We will talk about this. Whereas for WANs, a router is connected with another router using a link, a direct link. So there is no sharing or something like that. So this is PPP. Okay? So there is point to point. So whatever, as we said before, whatever information we'll send from here, it will definitely reach here. Right? So this is point to point communication. Whether a router to router, host to router, or a router to host. So I want to send information from here to here, so the data link layer will be responsible for sending information on each individual hub. As we said before, the physical address in the data link layer, okay, changes at each part, right? So this is one question that came in midterm. But again, I mean, maybe 50% did not do it quite right. So the physical layer is one of the things that changes at every single hub. So for every single hub, I have to specify this is the source and this is the destination. And then both the source and the destination, they will change in the next hub. That's why we say that the data link layer provides this point-to-point or node-to-node or device-to-device communication. Okay. So the data link layer has two major functions. One of them is that it allows the upper layer to access the medium using techniques like framing. From the upper layer, from the IP, we do we form a frame which is suitable to be sent over a particular medium. So the framing part is done with the perspective that this frame will be sent over Wi-Fi, or sent over wireless or fiber optics or and so on. Okay, so the framing itself varies depending on the medium. The type of framing varies depending on the type of the medium. And also it controls how data is placed onto the medium physically. So for example, this is, so Wi-Fi, it depends whether this Wi-Fi again is shared or you're providing like a point-to-point communication over wireless, or some shared medium like this. This medium has very interesting characteristics here. All of us are connected on one shared medium. This can be done physically using a hub or a switch. Everybody's connected to it. When everybody's connected to a device like hub, then this hub acts as a shared medium. This is what we call the logical topology of a hub. This is a logical topology of a hub. This is what the hub represents physically in reality. But logically, it looks like this. Anyone who sends, it will go to all other devices. Any device that sends anything, all the other devices will be able to listen to it. Okay? So if you send over a shared medium, well, you cannot use all Fs. You have to specify a specific physical address, right? So that's one thing. The other thing is that you want to control who places any information on that shared medium at any point in time. For example, if you and another one send information over the medium, what will happen?
Information will get together.
Will get together. Okay, so can you extract one from the other? Possibly not. Probably not. Right? So you need to make sure that the control to access the medium is done carefully. When two nodes get to access the medium at the same time, you cannot extract this information from the shared line. So you want to control when to access the medium. So that's another part of the data link layer which we will discuss in details in later chapter. So, so these are the two functions: framing, this is the service for the upper layer, and control when to access the medium or how to access the medium. So, so the data link layer prepares a packet for transport across the local medium by encapsulating it with a header and trailer, as we said. And the data link layer frame includes three major parts. The data, of course. The data is a layer 3 IP packet, normally. The header has control information such as addressing, and it has other fields as well, which we will discuss. The trailer will have control information such as error detection, and in some cases, error detection and correction as well. So by correction, we mean that not only do we know that there is an error in the packet, but we know where the error is. If you know where the error is, you can correct it, because the bit has two states, right? 0 or 1. So if you know that this bit has an error, you toggle. If it's 1, convert it to 0. If it's 0, convert it to 1. So this is correction. So error correction is done by knowing where the error is. Okay? Data link layer govern how to format and frame and use on different medium, and this is the first layer, as we said, that starts to care about what the medium looks like physically and what are the characteristics of this medium, whether it's a wired medium, a wireless medium, or a fiber optic medium, and so on. So at each hub along the path, an intermediary device accepts the frames from one medium and decapsulates it, the frame, and then forwards the packet to another medium. So the data link layer has to decapsulate and regenerate based on the next medium. So at every hub, you have to encapsulate based on the new medium. Okay. So the data link layer is the one that addresses this issue. So IP doesn't care, with the only exception of fragmentation. So it knows that whether it needs to fragment or not. But the data link layer is the one that deals with the characteristics of the medium. This is shared medium, this is the point-to-point, this is fiber optic, this is wireless, and so on.
Even if the medium is still the same, for example, after the first router, the second medium after the router.
Yes.
It will also decapsulate?
Yes. You have to do that for every single hub. You have to decapsulate and recapsulate. Why is that? Because simply you have to change the physical address every time. Right? So regardless of whether the medium changes or not, you have to decapsulate and recapsulate. And in doing this, of course, you eventually, as we will discuss in the physical layer, on the medium, what you actually send on the medium is analog signals, right? So what the data link layer does is that the physical layer, it converts the analog signal to digital, and then you will be able to regenerate another signal which adapts itself to the type of the medium. Whether it's wireless, you'll be talking about electromagnetic wave, and so on. So every hub you have to do this. Okay?
At this point, the signal is analog, not digital, right?
At this,
At this point, which is the data link.
No. I didn't say that. No. The physical layer is the one that deals with analog signals.
Okay.
Actually, part of the physical layer, not the whole physical layer. Part of it. We'll study that in next chapter. The data link layer still deals with ones and zeros. Okay. But as I said, depending on the type of the medium, the framing itself will put some information which is suitable for that type of the medium. Depends on the medium. Of course, there is some error detection techniques that needs to be done. Addressing has to be done, whether there is like shared medium or point to point, and so on and so forth. All this information will be taken care by the data link layer. So the data link frame has the addressing and the type and the quality control. So the typical field types are start and stop. The start and stop here, this is the frame start, and this is the frame stop. The frame start and the frame stop here. Remember that for the physical layer, the physical layer deals with stream of bits, right? So for the physical layer, there is a continuous stream of bits. So what tells the data link layer that this is the start of a new frame and this is the stop of a new frame? Okay, so that's what this field is for. So when the data link layer receives the bits from the physical layer, it will be like stream of continuous ones and zeros. Okay, so how would I know that? Starting from here, I have a new frame, and this frame will end here. Okay, so this is the important function of this frame start and frame stop. The frame start and frame stop, these are information that gets generated from the physical layer. Okay, when it sends these bits to the data link layer, the physical layer will tell the data link layer, this is the stream of bits that I have received, and the data link layer will then say, this is the start of a new frame, this is the stop of a new frame, and after that there is a start of another frame, and so on. Okay, why I need to have a start and stop? Well, for two reasons. One reason is because of course the frame in general could have a variable size, right? So even if you have stream of bits, you have start frame, and then you have a frame of a different size. It could be X, could be Y, whatever. So I need to have a stop frame as well to tell me that this is the end of that frame. And then and only then I can read this frame, and I can extract the header and trailer and start processing the packet. The other reason is that sometimes the physical layer will give me a silence period. Silence period will be like noisy packets or bits, which could be all zeros. So how would I know that there is a stream of zero, which whether it belongs to a frame or does not belong to a specific frame? Okay, so sometimes the medium itself gives you some noise signal which can be interpreted by the physical layer as all zeros. So this goes to the data link layer, and the data link layer will say, okay, this is not a start of a new frame, so these bits I don't have to process. Okay, so the typical parts of the header and trailer are start and stop. addressing fields, and these addressing fields are physical address fields. The type field, which again is used to tell the upper layer which protocol I need to access, and in many cases this type field would have a value that indicates IP. And there is some quality control packets that depends on the protocol, whether it's Ethernet or frame relay. Depending on each protocol, these have different functions, which we will talk about. And then the data field. So this is much simpler compared to all the other protocols that we talked about before. Okay. Okay, so we'll stop here.